Okay, so to finish out chapter 4, what I want to do is I want to go through the Boltzmann figures that they have right here. There are two different situations that they show for the Boltzmann figures. This one shows the difference between an endothermic and an exothermic reaction. So you want to put these together. This has a very clear picture of the Boltzmann distribution right here. Remember that the Boltzmann distribution is a e to the x function. That's why it's curved like that. And it shows how many molecules are in which energy levels. So of course you usually have the most molecules in the lowest energy levels. But the real question is how many molecules are in the higher energy levels. These are two different cases with two different A to B reactions. A to B is endothermic. This is what an endothermic looks like. And this is actually these are both endothermic reactions. Because if you look at the lowest energy level in each one, A and B have identical lowest energy levels, right? The thing that's different is the spacing of the energy levels. The location of the lowest energy level is related to the delta H. Okay? The heat that will be given off when you go from A to B means that is how much energy do you step up when you go to A to B. The entropy is something different. The entropy has to do with the spacing of A to B. The entropy is how many levels are accessible once you get to B or once you get to A, okay? And so that's why A and B here have similar entropies. They have similar spacings of energy levels. But B is a lot higher energy than A. So this is an endothermic reaction. It takes energy to push your molecules from A to B. At equilibrium, what you'll have is you'll have a distribution, and they'll actually, the Boltzmann distribution is the same. It just depends on what energy levels it fills up. But you see that the red A has a lot more energy levels filled up because they're lower in energy. And so you end up filling up the energy levels from the bottom up according to the Boltzmann distribution, and you just fill up a ton of the A ones before you even get to the lowest B level. So there's a little bit of B around, but there's not much because it's higher energy, more unstable. You have more of the A because it's more stable, and it's not just the stability, it's also the probability, the number of different similar states that there are, and that's reflected in the spacing. The spacing of levels is about the same in each one. If that's the case, the only difference is that B is higher energy than A. However, what if you have a big difference in the spacing? And that's what's on the right here. Here you have the same delta H. The A and B levels have the same relationship. But you have very different S's for each one, okay? The B has a much higher S. There's a lot more ways to be in B that are a lot closer together. The lowest one is higher than A, but for A, the lower level gets filled up, and there's only, it's like the hotel's full, and there's much fewer molecules in A, whereas if you look at that Boltzmann distribution, you only have a certain number of molecules, and by the way, that's constant between these two, but the molecules fill up the levels, you know, in a different way for each one. There's the same number of molecules, but the question is, why do I have so much more B over here? It's because A gets full, and the levels are so spaced that by the time you get to the third level of A, you have like 5 levels of B. And by the time you get to the fourth level of A, you have like 24 levels of B. And so the B fills up the energy, even though it's at the tail end, the small tail of the Boltzmann distribution. There's so many levels, and there's so many ways to be B that are very similar in energy. That is the idea that B is more spread out, in a sense. Spread out means, in this case, that you can occupy similar energy levels. It can spread out over closely related energy levels. So that's the one thing I want to be clear about. Entropy is about the molecule spreading out. And in B on the right, it is able to spread out into more closely related energy levels. The energy levels themselves are actually closer together. But we don't care about the energy levels. We care about the molecules. And so the molecules in B can spread out over more closely related energy levels. Therefore, you have more B. The A, you have a couple of conformations, a couple of energy levels that do have a lot of A in them, but you have many more energy levels that allow B to be B. And that energy fills them up until you're all out of molecules. So at a certain energy, you'll actually have more B than A, even though the delta H is positive. You have to go up to go from A to B, right? The delta H is that relationship, but the delta S is how many states there are. And if you think about it, if I change the Boltzmann distribution, if I change the temperature, what's going to happen to the Boltzmann distribution? The bottom will shrink and the top will grow. It's going to go like this. And that's going to let you have even more B, okay? So putting temperature in to the equilibrium will end up giving you more B for an endothermic reaction. This is often taught as Le Chatelier's principle, but notice that I haven't said it. It's actually, I think it's better to depend on Boltzmann than to depend on Le Chatelier. I guess that's not a general preference for German over French, but French are better at food, but this German is better at explaining why temperature makes some things go. The other thing to look at is, this is another same idea, but here we have, before we had S being different, here we had the spacing being the same, and we had a positive delta H. This one actually has a positive delta H and a negative delta H. Which one's the negative delta H? You can point for me. It won't be recorded. Which one's the negative delta H, left or right? Yeah. Yeah. Yeah, exactly. And you can see that the A, if you're going from A to B, you're going down. So it's negative on the y-axis. It's a negative change. And therefore, it is exothermic. Before, we had two endothermic reactions with different S's. Now we have an exothermic reaction, endothermic reaction, with the same delta S, because the spacings are exactly the same. But this shows you what's going to happen. This shows you how to think. I walked you through how to think about how temperature is going to change the Boltzmann distribution. This is showing it to you in Atkins compressed into the margin kind of way to do it, which is what I find annoying. So that's why I want to tell you. The low temperature is the blue line. It's more shifted this way. When you shift high temperature, it's going to go like this. Less down here, more up there. And that means that actually as you shift to higher temperature, you're going to get more B, less A. You're going to get less of the stuff that's on the bottom. For an exothermic, as you fit to higher temperature, you're going to get more A, less B, because there's more of A on the top, more of B on the bottom. Basically, if you shift temperature, you get less. Increasing temperature gives you less of what's on the bottom, more of what's on the top. Exothermic, endothermic tells you what's on the bottom and what's on the top, if the spacings are similar, okay? If you can go over these and think about them and relate these diagrams to those equations, you're going to do great on the test, okay? And you'll have your book for the parts you forget. So if you want, or if this just blows your mind, you're just not a graphical thinker, okay, well, skip that problem. You'll have that option, all right? But I wanted to give you that chance. This one? Yeah. Yeah, I mean, this is actually A, or figure 4.6, is exactly the same as figure 4.11a. The only difference is what you're comparing it to. Remember that this one is an S comparison, this one is an H comparison. Okay? I think these are really good figures if you would just actually let them grow, you know, to the size they're supposed to be. Some days I'm going to have word with Atkins. But anyways, we have philosophical and theological differences. He doesn't think theology is a category that deserves to be talked about with differences, and I disagree formally. But anyways, but he's a very good physical chemist. Yeah, I'll leave it at that. So, okay. But this is how energy moves. When you're talking about raising the temperature and seeing a reaction change, the energy is changing the temperature. The random heat motion is changing what happens. And you can talk about that in terms of H, S, and G. And so all of these things have to do with questions of energy moving. And I literally am going to just introduce this, and I'm going to drop it, and then we're going to pick it up again on Friday. But the thing is, I picked this diagram because usually pressure units are all over the place. What I like about this is pascals. And so you can actually figure out how many pascals. I think 10 to the 5th pascals is about where we are today. And I know around 300 temperature is where we are today. We actually we're at this point today, which is in the liquid island, but close enough with a small physical change to have vapor and solid present in reasonable quantities. I would argue that being in this point, being too far this way means the planet would freeze over and we'd only have a little bit of liquid water. Too far this way is gas giant. So being at this point, and the thing I want to point out, every phase diagram, the liquid is the hard state to be. It's easy to be solid, easy to be gas. It's hard to be liquid. The planet started out as hot and high pressure. Then it lost pressure and it lost heat. And it cooled down, but it didn't go too far because zero's out here. It'd be easier for it to, somehow the planet, and I think this was really important for life, the planet moved and moved and moved and moved and then kind of stopped right here. Because there were geological processes and later biological processes that actually kept it, even though stuff was fluxing and changing, kept the planet at this temperature and this pressure close to the triple point. And I think that that's an important physical chemical principle for life because I think you need all three phases for life. Water is constrained by the phase diagram to be liquid at standard temperatures and pressures. And that's actually a special place to be on the graph. So we can think through all these things, and we can look at heats of formation and delta G's of formation. And for example, heats of formation, these are all pretty similar in entropy, so we can look at heats of formation alone. And we can take the heat of formation for different diatomic salts versus ions. And we can see that there are trends that fit into single lines for the same atoms in a crystal, or just as two atoms, so like a repeating crystal, just two atoms, or being dissolved in water. And the thing I want to point out about this is the radius of this has to do with the atomic sizes, which is set by the periodic table. The atomic sizes follow a straight line because the periodic table builds these up in a straight line, by certain numbers of protons, and then it repeats in certain patterns. And those patterns change the energies for being in the different states. The relationship of the energy of being in a crystal versus being in an aqueous ion is otherwise known as solubility. We can write a solubility equation. We can get a K for that. And we can express how much it wants to be in a crystal versus how much it wants to be in water by itself. But that has to do with periodic trends as well, because you see there is a straight line between the energy of the interaction and the radius of the interaction, just like with general bonds. So we're going to be able to see some patterns, and they're going to be related to some trends related to size, which is related to the periodic table. And this right here is the actual chemistry data that I couldn't put into A World from Dusk because it was too mind-blowing. But here are the three ways of having it. But having a sphere of that size and that charge, once you have it ionized, will be a particular energy, and they all have the same charges or similar charges, and so they all behave the same relative to each other. If you have spheres that can pack together better, you'll have a better crystal energy. And if you have a sphere that is a different size, it will interact with water about the same as another sphere of the same size. So this shows that we're all just talking about charges in water, but there will be some things that are very happy, very stable in the crystalline form, less stable in the water form. And that's what we mean by solubilities, okay? We can write a solubility. I will start here with this, but this is a reaction, precipitate to ions. And the only thing about the precipitate is a solid. What value does it get in K? A pure solid or liquid is just it ends up dropping out of the equation. Technically, it's 1 because it is a ratio. So to make it drop out of the equation, you make it 1. But you don't ever see it, just like you never see 0. Okay? We will get into what this means. So these solubility numbers are universal, and they're very important to life, because if it can't get into that liquid phase, what's the point of having a liquid phase if it can't get into it? Okay. All right, so that will at least give you a start for Data Talk 1. We will end up talking about that at the end of Data Talk 1, so please look over that. Please work a little bit on the project, and I will see you on Friday.